Hello everyone, this is B. Veeramat. Today I am going to discuss another part of the current electricity here in which we want to discuss the concepts of current, drift velocity, Ohm's law like this. So first thing is conventional current. What is meant by conventional current here? The conventional current is a current whose direction is along the direction of the motion of positive charge under the action of electric field. See, which is explained as like this. Let us consider a conductor. So there are two free hands here. One end is with a positive potential, another end is with a negative potential. See here, we know the general concept. The electric current. Electric current means the flow of electrons or negative charge particles. But this is the concept of conventional current. Here the conventional current whose here in which the direction of flow of current is along the direction of positive charge. See, that is nothing but here conventional current is nothing but it is a current whose direction is along the direction of the motion of positive charge under the action of electric field. So as the given shows, the figure shows like this. Here there are some positive charges. The direction of flow of current along the positive direction, nothing but from positive charge to negative charge. So that if the charge flowing from positive charge to negative charge, this type of current we can call it as conventional current. So one more is electric current. Here the electric current is nothing but that is a type of current there in which the electrons are flowing from negative potential to positive potential. That is an electric current. Then conventional current is due to motion of electron in the direction opposite to that of the motion of electron. See here, actually instead of electron we are considering here as a protons. This is about a conventional current. So the conventional current and the electric current, there is a difference like this. In conventional current, the charge particles flow from positive to negative side, positive potential to negative potential. But in electric current, so electrons are moved from negative to positive potential. So this is the difference between electric current and conventional current. See, there is a why it is confusing. Actually, it is not confusing. One more time, I am explaining about the conventional current and electric current or electron flow of current. See, the conventional current assumes that the current flow out of the positive terminal through the circuit into the negative terminal of the source. This was the conventional current. Convention choose during the discovery of electricity. Actually, this was the wrong theory. But they thought that the current or charges which are flow from a positive terminal to negative terminal. The next, after discovery of electron, they were concluded one more theory, that is electron current. Here, actually what happens means the electron flow out of the negative terminal through the circuit into the positive terminal of the source. This is actual flow of electrons in the circuit. The both conventional current and electron flow of current are used now. The many textbooks are available in the both formats, conventional current as well as electron current. See, actually in fact it makes no difference with the way current flowing in which direction. See, as long which is used consistently, the direction of flow does not affect what does the current. Okay, so direction is doesn't matter here. The actually what we say, the changing from conventional current to electron current, actually the earlier they are using the conventional current, but nowadays after the theory of electron, electron current is developed, but The changing from conventional current to electron current was which caused the degree of confusion for older and new students with somewhat error. So the conventional current was kept assured. There was no confusion with those already trained with the conventional current. The two systems may seem confusing, but as long as the usage is conventional current only, but it is not real. Next thing, Ohm's law. See, Ohm's law statement is like this: the current I through the conductor is directly proportional to the potential difference across the ends of the conductor, the provided the temperature and physical conditions remains constant. This is the statement of Ohm's law. See here, Ohm's law is one of the very important and basic concept in the current electricity. One more time, I am explaining the statement. Ohm's law states that the electric current I through the conductor is directly proportional to potential difference V across the ends of the conductor, provided the temperature and other physical conditions remains constant. So as per the definition, this is an equation. So the current through the conductor, which is directly proportional to potential difference across the ends of the conductor. Then, or you can write this expression like this. See here, V which proportional to IR, where R is the proportionality constant here. So after removal of proportional sign, you should write proportionality constant. That is called as electric resistance. So as per this equation 1, the resistance can be written as R is equal to V by C. So I send it to LHS side, then it becomes R is equal to V divided by I. The definition is like this. The electrical resistance of a conductor is defined as the ratio of, see here, these are the ratios. The ratio of the potential difference V across the conductor, ends of the conductor, to the electric current I through it. That is the definition of electric resistance. The electric resistance also defined as electric resistance nothing but the opposition offered by the conductor or a material to flow of current. That is the definition of, one more definition of electric resistance. Resistance nothing but is an opposition offered by the material to flow of a current. That is the resistance. One more definition. See, the SI unit of resistance is ohm. The SI unit of resistance is ohm. So, which is represented by omega. Then the resistance of a conductor is 1 ohm. If, when means 1 ampere of current flows through it, when the potential difference across the ends of the conductor is 1 volt. See, if the ends of the conductor shows 1 volt potential difference, in such a condition, if 1 ampere current flows through it, then it's said to be 1 ohm. See, 1 ampere of current flowed through it when the potential difference across the ends of the conductor is 1 volt. Then it is, we can call it as resistance. Ohm, definition of ohm. See, the electrical resistance of a conductor, which depends on 3 factors. See here, it's very important. Many times it is in a annual exam, it's a 2-mark question, 2 to 3 mark question. On what factor the resistance of a material depends, or resistance of a conductor depends? See, the question is like this: on what factor the resistance of a conductors depend? In which this answer is, first one, it's material. See, the resistance of a conductor depends on material. What type material is? So whether it's the insulator or somewhat like it's a rubber, plastic, metal, like that. So if it is a metal, it's a very good conductor, then its resistance is very less. If it is a plastic or a rubber, then in such a condition its resistance is more, like that. So the resistance of a conductor which depends on the material. The next thing is, on second factor is the dimension of the conductor. See, which is the resistance which is also depends on dimension. So that will explain in the next concept. And which is depend on the temperature. See, so the resistance which is depend on the temperature also. If the temperature is more, obviously its resistance is more. How means? So as temperature increases, the atoms in the conductor which starts to vibrating more, and the free electrons which movement, so free electron movement is also increases. As moment increases, see what happens here, the collision is increases. So because of the collision, the resistance also increases. That is a third factor. So as per the second factor, see here, the dimension of the conductor, the resistance which is also depend on dimension. How means? See in the next concept, the resistance R of the conductor of a certain material at a certain temperature, it found to be directly proportional to length. See here, this is a dimension. How that resistance depend on dimensions means like this. Here this is an explanation. See here, the resistance R of the conductor of a certain material at a certain temperature is found to be directly proportional to length of the conductor and inversely proportional to its area of cross section. See, if the length increases, the resistance increases. If the area of the conductor increases, the resistance decreases. That's why, so that says the resistance is directly proportional to length and inversely proportional to area of cross section. So from that, there is an equation like this. R is directly proportional to length. Resistance is directly proportional to length and resistance is inversely proportional to area of cross section of a conductor. Or this expression can written as R is equal to, so instead of proportionality sign, we wrote a proportionality constant, that is rho. Then R is equal to rho into L divided by A. This is equation number 2. Where the proportionality constant rho is called as resistivity. Resistivity we can call it as specific resistance. That is called as resistivity. The resistivity of a material which is depend on the actual resistivity depends on the material of the conductor and temperature, but not on the dimension. See one more time, one more here. The resistivity which is depend on the temperature and material, which does not depend on the dimension. Using this expression R, using this expression of R, Ohm's law can be written as. So we know that V is equal to IR. This is the Ohm's law, and I keep as it is. R means we have the value of this. R is equal to rho L divided by A. This is the value of R from the equation number 2. The electric current per unit area taken normal to proportional of the conductor. See, the electric current per unit area, so taken normal to the direction of the current, is known as current density. See here, this is after third equation. So there is one more important definition is there, that is current density. See this equation. The current density which is represented by the symbol J. So according to this, see here, J is equal to I divided by A. Nothing but the current. So from this equation, we can define the definition. So current density is equal to, that is electric current per unit area, normal to the direction of current. This is the definition of current density. The current density is defined as electric current per unit area taken normal to the direction of a current is known as current density. This is the definition, and according to, so this definition equation is J is equal to I divided by A. See, one more time, I'm defining the current density. Current density is equal to electric current per unit area. So take a normal to the direction of current. This is the definition of current density. See, its SI unit is ampere per square meter. So this is say, so we can write like this: ampere per square meter, and current density is a vector quantity. And the next thing is, if E is the magnitude of the uniform electric field, if we represent E, we know that, so from the first chapter we learned the concept. E means the magnitude of the electric field that is developed in the conductor. See, if we consider a conductor, there are two ends. So one side is a positive potential, another side is a negative potential. In such a condition, the electric field is developed inside the material or a conductor. So from positive potential to negative potential. So that is E, which is represented here. E be the magnitude of the uniform electric field. Then uniform electric field in the conductor whose length is considered as a L. V be the potential difference across the ends of the conductor. Then, so in the second chapter we learned there is a relation between electric field and potential. See, so there we studied that concept. The relation between electric field and potential is E is equal to V divided by L. So we learned that concept in the second chapter. That is relation between electric field and potential. As like that. So see here. This is an expression. So the relation between electric field and potential. So according to that, electric field E is equal to electric potential per unit length. So that is V divided by L. Or that equation can be written as V is equal to EL. Thus, from equation number 3, actually this is equation number 3. From equation number 3 says V is equal to I rho L divided by A. So from equation number 3, so instead of V, so in place of V, we can write this value. Instead of V, we can write this value, I rho L divided by A. So EL keep as it is. Instead of V, we need to write I rho L divided by A. After that, there are some terms there are some terms here. That is one more term, one more definition is there. That is, we know that J, current density is equal to current per unit area. But here we have area per length. Sorry, yes. Here there is a, according to definition of current density, that is a current per unit area. So that instead of I by A, we will write J, then rho and L keep as it is. Then L get cancelled, remaining term E is equal to rho into J. So this is an expression for electric field developed inside the conductor. Since the direction of electric field and density are same, then equation 4 can be written in the vector form as like this: vector E is equal to vector J into rho, or vector J is equal to vector E divided by rho. Then 1 by rho, reciprocal of resistivity. See here there is 1 by rho is here. The 1 by rho means that is a reciprocal of resistivity is conductivity. So resistivity means opposition to flow of current. Conductivity means which allow to flow of current. That's opposite word. Hence 1 by rho, reciprocal of resistivity is equal to conductivity. Hence J is equal to sigma E. 1 by rho means sigma, then vector E keep as it is. This is the equation of the conductivity. So rho, sigma is equal to 1 by rho, then current density expression can be written as sigma into electric field. This is the concept of relation between current density and conductivity, and this is the relation between current density and resistivity. See, one more, that is if the relation, if they ask like this, if the what is the relation between electric field, current density and resistivity, means then this is an expression, we can write this or this. If it is in terms of conductivity, then you need to write this equation. Next concept is drift velocity. Drift velocity, nothing but its definition is like this. The drift velocity is defined as the average velocity with which free electrons get drifted towards the positive end of the conductor under the influence of an external electric field. This is the definition of the drift velocity, or you can define like this. The drift velocity defined as the average velocity with which free electrons get drifted towards a positive end of the conductor or opposite to the electric field under the influence of an external electric field. This is the definition of drift velocity. So according to this, let us consider a conductor. This here, this is the conductor. Then one end free, there are two free ends here. One end of the conductor is connected to positive terminal, another end is connected to negative terminal. So inside the conductor, there are so many free electrons are available. Those free electrons, actually in absence of electric field, so if you are not applying the potential in such a condition, so these electrons or free electrons which are moving with a random direction, if once potential difference is applied, then so this end is acts like a positive end and this end is acts like a negative terminal. Then these electrons are the negative charged particles which are attracted towards positive side with some velocity. Then the average velocity of this electron, that is what we can call it as drift velocity. See, drift velocity means the average velocity with which free electrons get drifted. See, drifted means jumped. So which are drifted towards the positive terminal. This is the positive terminal. Drifted towards the positive terminal of the conductor. So this is one definition. Or the average velocity with which free electrons are drifted opposite to the electric field. See here, electric field direction from positive to negative. In this direction there is an electric field. That these free electrons are drifted opposite to the electric field. You can define like this also. This is the definition of electric field. There is a important derivation of the drift velocity, that is a 3-mark question in the annual examination. See, the derivation of drift velocity. Let us consider a metal conductor. See, let us consider a metal conductor has a large number of free electrons. It's about 10 to the power 29 per cubic meter. So within 1 cubic meter, there is a 10 to the power, approximately 10 to the power 29 free electrons are available. Then at room temperature, these electrons are moved randomly, normally without applied the potential difference. With due to temperature, these electrons move randomly within the body of the conductor, like molecules of a gas. This is due to collision. They suffer with a heavy collision. Because of the random motion, these free electrons get collide with each other with a heavy and fixed ions. The directions of these free electrons are also randomly distributed. So the average velocity of the electron is 0. So because of the random motion of the electron, the average velocity is 0. That is represented as like this. So the average velocity, so V1, so velocity of the first electron, velocity of the second electron, I value is taken as 1, 2, 3, first electron, second electron, third electron, like that. The average velocity, so average is taken summation you can take it as a summation divided by total numbers. See, the sum of all numbers divided by total numbers, that gives the average. So that's why expression is 1 divided by n number of electrons. I is velocity of the summation of velocity of all electron from 1 to infinity or 1 to n. So the average is equal to 0. Then when the some potential difference is applied across the ends of the metal, see, so it's till we discussed about the concept in absence of electric field. Now if you apply the potential difference, if you apply some voltage, then in such a condition, see, some potential difference is applied across the ends of the metal conductor, then electric field is set up inside the conductor. See, already told that if potential difference is applied, this is actually like a positive terminal, this is actually like a negative terminal. Then electric field is generated inside the conductor. As a result, free electrons in the conductor experiences a force in the direction opposite to the electric field. See, so if the electric field is developed, we know that electric field means, so the space around the charge. So for example, the space around the charge, so if another charge is entering into that space, see here, this is the space of electric field. If the charge is entered or if the charge is present inside that electric field, which experiences a force. Now the experienced force is attractive force, because this is a positive potential and electrons are negative charges. So which are there is a, if unlike charges are there, then attractional force between them. That's why these electrons are drifted towards positive terminal. Then so the force on the electron in the electric field is equal to F, this is the expression, F is equal to minus E into capital E. See, this is a definition we already learned in the first chapter. So in the first chapter, electric field definition is like this. Electric field is equal to force experienced by unit positive charge. Here the charge is electron. So this is the definition of electric field. Electric field means force experienced by the electric charge. That's why then, so you can, if you want force, now, that's why F is equal to E into capital E. But why it is negative sign means, here see, electric field and the flow of charge are in opposite direction, which is represented as a negative sign. That's why force is equal to minus charge into electric field. Then due to this force, electrons are accelerated in the direction opposite to the electric field. So due to this force, electrons are accelerated towards the positive terminal. Then so the acceleration of the equation is, we know that F is equal to, first year you learned about the concept of force, F is equal to ma, then A is equal to F divided by m. See, A is equal to F by m, that is equal to, F means we know the equation, that is minus E into E divided by m, keep as it is. This is equation number 2. Here where m is the mass of an electron and E be the charge of, minus E be the charge of the electron. On their way, the accelerated free electron suffers a frequent collision against the fixed ions of the atoms. See here, there are in the conductor, there are some fixed ions or fixed atoms are there. So due to drifting, those electrons which suffers a frequent collisions. So because of the collision, so what happens? The electron is moving. See here. So this electron is moving with a somewhat velocity. If which is collided to the one atom, then its kinetic energy mu. So with the energy, there is a kinetic energy is obtained due to motion, and that if immediate after collision, the kinetic energy becomes 0. So its velocity, if its velocity is 0, its kinetic energy is 0. That's why after collision, the free electrons gains actually after collision there is a loss of kinetic energy. Then again that accelerate because of the acceleration, because of the attractional force, again the kinetic energy gain takes place. Then the energies next collision, till next collision, the energy increases are obtained. Then this process continues till electron reaches the positive end of the conductor. That's why let vi be the velocity of ith electron at any instant of time t. See, vi be the electron velocity of the ith electron at any instant time t. If vi was the velocity of the electron just after collision, see, this is the capital V and this is the small v. There is a difference. So vi means velocity of ith electron at instant time t. Then small vi was the velocity of the electron just after collision. This is the velocity just after collision and this is the velocity at a time t. Then so that is a velocity just after collision at a time ti is the time elapsed after the last collision. Then velocity vi at any instant time t is equal to that nothing but it is a final velocity. This is an initial velocity. In first year we learned the concept of v. V is equal to u plus at. There is a formula in the first PUC. V is equal to u plus at formula. According to that, see, here this is an expression. V is equal to u plus at. So v means final velocity, which is represented at the time t with respect to time t, and here in place of u, this is the velocity just after collision, that is taken as a vi. Then a means acceleration, we already took from this equation. A is equal to minus e, capital E divided by m. So this is that, and t be the time. Since the electron was accelerated for a time t, the average velocity or electron at a time t is the average of vi of all electrons, but average vi for all electrons is 0. See, just after collision, velocity is for every electron, that average is equal to 0, since the direction of velocity of electron immediately after collision is completely random. See here, actually if electron is moving with velocity v, then there is some fixed atoms that electron is colliding to that one, then immediately its velocity becomes 0. But this positive charge again attract the electron, that's why the velocity again increases. That nothing but immediately after collision, the velocity is the electron moving with some random direction. That's why average velocity immediate after collision is equal to 0. That is represented here. The average vi, nothing but velocity immediate after collision for all electron is 0, since the direction of velocity of electron immediately after collision is completely random. Moreover, the collision of an electron do not occur regular interval of time, but at random times. Not regular interval. Collision may be in random times, not a regular interval of times. The average time between the two successive collision, that is with electrons with the fixed atoms in the conductor, is defined as, that is a definition of relaxation time. See, so for example, if an electron starts actually if an electron collides here and immediately collision, its velocity becomes 0, then again it is accelerated, then come to the second collision here, then the time elapsed between these two collision is called as relaxation time. See here, relaxation time means the average time between two successive collision of an electron with the fixed atoms in the conductor is called as relaxation time, which is represented by tau. The taking the average value vi as a vd, the average value of vi can be considered as a vd and average ti can be considered as a tau. Then equation number 3 becomes, this equation becomes instead of vi we can write vd, that's why this is vd. Then average velocity is 0, that's why this value is 0 here. Then minus e divided by m, keep as it is. Then instead of tau, average time taken as a tau, or vd is equal to minus e, capital E divided by m into tau. This is an expression for drift velocity. So this is an expression for drift velocity. It's a very important for 3 marks. Thank you everyone.